It's hard to believe that so much of our modern world was sparked by a remarkable group of Scottish engineers, men who prospered in a cauldron of colossal change.
The sense you get from these men is that everything's possible.
The Industrial Revolution of the 18th and 19th century saw Scots of unique intelligence apply their ideas to the world around them.
You would walk straight past it without realising it, but this is the single thing which changed the world.
Our world is indebted to men like James Watt for his steam engine, John McAdam for our modern roads, and Thomas Telford for his vast legacy of bridges, aqueducts and canals.
It's said that he advanced civilization by a whole century.
Biggest, strongest and longest was their credo. Bridges, lighthouses and ships were enduring symbols of their faith.
They became, if you like, the new high priests of technological change.
Scottish engineers pushed boundaries, expanded their horizons. They tested materials to the limits, and for some, their labours reaped huge rewards.
I sell here, sir, what all the world desires to have: power.
Scotland had travelled far since the Treaty of Union with England in 1707. In the last quarter of the 18th century, Scotland was accessing the riches of England's vast empire, but also benefiting from its technological advances.
England industrialised before Scotland, say 20 years before, so they had that experience that could be brought north, and that was particularly evident in the textile industry and also the chemical industries, which were the foundations of Scottish industrialisation in the 18th century.
Scotland was changing irreversibly, and while not blessed with abundant natural resources, it used any available means to advance.
What the Scots had was brain power. They also engaged in industrial espionage in a large scale. Scotland a bit in the 18th century were like the Japanese in the 20th century. They would steal ideas from anybody and improve them and work upon them. So the growth of Scotland was actually indigenous entrepreneurship and technology.
Throughout the 18th and 19th century, Scotland industrialised at an unprecedented rate.
Let's not forget that the Scottish Industrial Revolution was the fastest in Europe until forced Soviet industrialisation of the 1920s.
And the driving force behind this accelerating industrial world would be steam. To perfect the harnessing of steam power would forever end the reliance on wind and water. And it was in 18th century Scotland that the technical brilliance and vision of one man would change the world.
James Watt came from quite an interesting family background. He was born in Greenock. His grandfather was quite an important mathematician in the town, and his father was an instrument maker.
Despite little formal education, Watt followed his father into instrument making. Serving his apprenticeship in London, he returned north to work at Glasgow University in 1763. Impressed by his skill and ingenuity, Watt was asked by the university if he could repair a model of a then state-of-the-art steam engine designed by Thomas Newcomen.
He fixed it, but it was incredibly inefficient. It needed masses of coal before it would work at all, and then it stopped working after about 30 seconds. And he worried about this for a long time, for months. Actually months he worried about it. And then one morning, this is May of 1765, he had this flash of inspiration. And this is one of those eureka moments, of which there are maybe a dozen in history.
Watt's moment of genius was deciding to add a chamber separate from the cylinder where steam could be cooled. This would allow the piston cylinder to remain the same temperature as the entering steam. No energy would now be wasted reheating it and the water inside. After 4 years of hard graft and testing, Watt perfected the steam engine with what he called the separate condenser.
This is Watt's original separate condenser model from 1765. It's such you would walk straight past it without realising it, but this is the single thing which changed the world. This is the original apparatus with which he proved that the separate condenser works. and as such was the basis of his whole career and the whole, the exponential growth in steam power.
Making it less hungry for huge amounts of coal, Watt's innovation had trebled the efficiency of the steam engine. The impact of the separate condenser was immediate and profound in Britain's industrial future.
With the rise of steam, technology becomes the driving force of the economic thinking. Scotland does not have a large population, but it has invention and it has technology, and it can apply that technology. So Scotland is at the forefront of this shift away from labour towards technology.
Now, for the first time, somebody other than a coal mine could afford to run one. They could afford to use these engines to drive machinery, which had never been done before. And so they could start running mills, great cotton mills and woolen mills, by steam engine power. So this absolutely transformed the Industrial Revolution.
The technological advances made by Watt were not lost on those whose leanings towards innovation were driven by the bottom line. Watt was soon to attract the attention of English entrepreneur Matthew Boulton.
He really respected Watt. He realised that Watt had a lot of very good scientific backing and a good grounding and knowledge about science. Boulton saw something in him and they created a very successful partnership.
Now, it took them some time to start making money, obviously, but nevertheless, they knew what was going to happen. And his partner, Matthew Boulton, boasted, "I sell here, sir, what all the world desires to have, power."
English finance combined with Scottish innovation made Boulton and Watt's company the first engineering powerhouse in Britain. Based in Birmingham at their Soho foundry, both men grew rich from supplying their engines to eager industrialists for £850 apiece, equivalent to almost £1 million today. But the introduction of the steam engine into the workplace also signalled vast social upheaval.
The steam engine is the progenitor of a quite different way of working, and it introduces what you would call the discipline of the industrialised society, which has never left us. So time becomes transformed. People just can't take time off when they wish to. The machine is lord. The time when you could move between different tasks on the land, and that the tasks on the land were partly related to climate and to sun and to shade and to rain, that's all gone. It's not surprising that these new factories were first likened to a combination of prison and poorhouse.
Watt patented his invention in 1769, 6 years before he went into business with Boulton. But his partner's sharp financial mind would ensure that it would fully exploit the power of this patent. Persistent lobbying of Parliament allowed Watt and Boulton to extend their monopoly to an unprecedented 25 years.
It was obviously good for Boulton and Watt, but it was very bad for the development of the steam engine because it meant that nobody else could make steam engines in all of that time. And that's a long time at the beginning of a burgeoning new industry.
It was during this extended patent that Watt was accused of clogging engineering enterprise for more than a generation.
There's certainly an argument that Watt, in his later years, was very rigid and very protective of his patent. The prime example of that is William Murdoch. William Murdoch worked for Boulton and Watt, was an incredibly loyal employee, and came up with a number of the items that were patented under Watt's name.
Despite groundbreaking inventions such as coal gas lighting and the sun and planet gear, which allowed the steam engine to run machinery in mills and factories, Murdoch was undervalued by Watt.
He wanted to make high-pressure steam engines, and Boulton and Watt said, no, it's a waste of time, we don't want to do that, and stopped him from doing it, which was a great pity. He'd invented a little steam carriage, and he was actually going to patent it in London, and he met one of them at Exeter. He'd come up from Cornwall, and the other chap was going to London, and Boulton said, no, sorry, we don't want to do that. You're our employee, put it away.
Despite this lack of desire to further advance steam power, James Watt remains one of the fathers of the Industrial Revolution and is still celebrated today. His technical ingenuity had a fundamental influence on how the modern world was shaped and developed. Yet his personal life reads in sad contrast to his scientific achievements.
In many respects, he's a really tragic figure. You know, his first wife dies, 5 of his 6 kids don't outlive him, and naturally, you know, death is one of these motifs. When you look at Watt's career, it just keeps coming back as one of the driving forces behind what he does. You look at the evidence which survives in Watt's workshop, which we have here in the Science Museum. So here we go. This is Watt's workshop. It contains approximately 6,500 items, which are together a complete sort of artifactual record of his entire working life. I think what this room does, it tells you more about Watt's character, because it's a very personal space. You know, you've got the stove down here, which is where he cooked his meals. He came up here, I think, to escape from his second wife, who was a bit of a she wore the trousers in their relationship. And there were all sorts of rather sad things in here almost. There's a chest which contains the sort of school notebooks and drawings and things of his son Gregory, who died of consumption, aged only 24. So again, you can imagine Watt coming up here really just to retreat from the outside world, to have a sit down and a gentle sort of.
James Watt was not the only engineer exploiting the power of steam. In the last quarter of the 18th century, men were pursuing a vision of steam-driven propulsion on water, but with little early success.
Lots of people drew drawings of steam engines fitted in ships. Some people managed to, install a steam engine onto an existing hull, and a few of those people managed to get it to crank over a few times, chug along a few metres, and then have some sort of accident like capsizing or flooding or blowing up.
But the real advance was to construct a viable and workable steamship. And it would be a precociously talented engineer from Lanarkshire who would become the true pioneer of this new age of transport.
William Symington was born into a family of mining engineers in Lead Hills in Lanarkshire. So he grew up surrounded by what was fairly new technology, working on the Newcomen atmospheric engines in the Lead Hills mines.
By the age of 22, Symington had constructed a model for a road-going steam carriage. Local mine owners had been so impressed that they funded his education in Edinburgh. There he met landowner Patrick Miller, who was developing double-hulled paddle boats. Miller saw the potential in combining the two ideas, and together they built a crude steamship that they launched on Dalswinton Loch in 1788.
Symington then took that experience and went off and developed another vessel, and for the first time in association with someone who was a specialist shipwright who would design a hull specifically to take his engine.
In December 1789, Symington launched his prototype on the Forth and Clyde Canal. It was the world's first demonstration of a practical steamship, and the vessel achieved the speed of 6 miles an hour, 3 times faster than a horse could drag a narrowboat.
Symington proposed that a steamboat could be constructed that would do the work faster and more cheaply. The trustees of the Forth and Clyde Canal weren't convinced, but they were willing to invest some money in investigating it.
But after that day in 1789, Patrick Miller withdrew his financial backing, and Symington was forced to abandon his project until the intervention of one man 10 years later. The Earl of Dundas was one of the most powerful men in Britain. He had business interests in the east and west coast of Scotland and was the governor of the Forth and Clyde Canal. He saw the commercial benefits in quicker transit of his goods through Symington's steamships.
One of the reasons why Scotland is a successful industrial nation is that the old elite behave like the bourgeoisie. Unlike in France, where the old elites were against this kind of developmental process, the old elites in Scotland lead it and are just as avaricious as the so-called specialists.
With the backing of the Earl of Dundas, Symington now forged ahead with his new ship, which he named Charlotte Dundas, after the daughter of his patron. The ship was launched in 1801.
It was widely reported in the press at the time. There was quite a gathering, and he must have thought that this was the start of something great for him and his new invention.
The excitement surrounding steam propulsion continued after another successful trial in 1803. But Symington's progress was to be suddenly halted, despite the influential backing of the Earl of Dundas.
The trustees of the Forth and Clyde Canal didn't have any inclination to invest further in the project because they were always very concerned that the wash from this steam-driven boat would damage the man-made banks of the canal. And there was also rumours that they had heavily invested in the companies that supplied the horses to do the towage. So they decided not to pursue the project further.
Symington never built another boat after the Charlotte Dundas, and history forgot his early promise. It was another Scot, Henry Bell, who would come to be considered the pioneer of steamships when he launched his Comet on the River Clyde in 1812.
Bell was a much better publicist. He was much better at arguing his case because he was an excellent businessman. Bell wasn't the inventor of any of the parts of his steam vessel, but he was the man who brought all these parts together and made them operate commercially.
Throughout his life, Symington fought for recognition for his pioneering work on steam transport. He lost all the money invested in his steamships and died penniless. He never witnessed the development of steamships into ocean-going leviathans. However, in the 1970s, Symington's reputation was finally revisited.
There was a really important book published in the 70s by W.S. Harvey and Gordon Downes Rose. They investigated his inventions, they looked at what he'd proposed, and as engineers they were able to evaluate his contribution, and they came out saying this man did lay the groundwork for everyone that came after him.
In perfecting the combination of steam engine and hull design, Symington was the individual most responsible for sparking Scottish shipbuilding traditions of the Clyde. The very term Clyde built, which became synonymous with excellence and the vast ocean liners built in the 1930s, are just elements of Symington's legacy. The development of steamships further demonstrated the science of engineering. But once at sea, all vessels, no matter how they were powered, could fall prey to unforgiving forces of nature. In the 18th century, the sea was the only link to foreign shores and trade. The coasts around Scotland were particularly fierce and deadly. For centuries, too many souls were lost to the ravages of the Scottish coastline. But one Scottish engineer took on our ferocious seas. Best remembered for the heroic construction of the Bell Rock Lighthouse, a lasting and shining beacon to progress, Robert Stephenson's engineering marvel still protects those at sea today.
If you were building a stone lighthouse in the middle of the North Sea or at the Atlantic, there simply wasn't the technology in existence up until that point to do it. So you had to improvise as you went along. They were effectively inventing a huge chunk of marine engineering science.
Combating savage weather and building on a treacherous rock that was covered at high tide. Robert Stephenson was attempting the impossible. Nothing so ambitious had been constructed before. He
was, A, forced to deal with the fact that they had to hop off every time the tide rose, and B, that there was nothing except what they could do manually. They were picking away at the rock physically with picks. He was having to deal with completely new and untried techniques and technology. Building a stone lighthouse in Scotland, where the seas were just that much more ferocious than down south.
But as the project was about to get underway, the trustees of the Northern Lighthouse Board had concerns over Stephenson's ability to complete the project.
I don't think people felt that Stephenson had the necessary experience to be able to achieve such a difficult project. This was the most incredibly difficult lighthouse to construct with the materials and equipment that they had at that time.
To help ensure against failure, the Lighthouse Board appointed the celebrated Scottish engineer John Rennie to oversee the construction.
In order to get the stones out there for the lighthouse, these were all pre-cut at Arbroath in a workyard, and they had a raised plinth in the yard which was 42 feet in diameter, on which each course of stones were cut and placed and then sent out to the rock.
As a feat of engineering, the Bell Rock was a daunting task. For every problem that arose, Stephenson and Rennie came up with bold solutions. An early crane hoisted the rocks on board, and a railway track helped shift these 3-ton blocks. Despite these innovations, constructing the lighthouse remained an enormous physical challenge.
It involved, shinning up cliffs, living on kind of cold, damp boats for weeks at a time, being seasick quite a lot of the time, I think, site visits at all times and in all weathers.
It's just an epic story. I think that's what catches the imagination, is the whole business of being wet and cold and tired and hungry and being subject to the elements and yet managing to continue.
After 4 years of unimaginable danger and groundbreaking engineering, the Bell Rock Lighthouse was finally lit in 1811. Its impact was immediate and immeasurable.
There is absolutely no question that they saved hundreds and hundreds of lives. I mean, if you take an example like Scarivora or the Bell, there would be an average of, between 1 and 6 ships usually wrecked on the reef, either of the reefs, every year. And as soon as the lights were built and lit, that stopped.
Robert Stephenson had built the impossible, but his determination to see this project as his lasting legacy would be to the detriment of Chief Engineer John Rennie.
However he may have felt about Rennie personally, Stephenson realised that Rennie was in the way of his path to professional glory. And Rennie was very deliberately elbowed out of the way.
Robert's relentless pursuit of self-advancement ensured history celebrated his achievements. But it was his eldest son, Alan, who would eventually outshine him.
The extraordinary thing is that Alan surpassed his father. He built, unquestionably, the most beautiful, most extraordinary, most perfect lighthouse, certainly in Scotland, probably in the world, Scarivora.
When it came to the design of the Scarivora Lighthouse, it was mathematically designed rather than the Bell Rock, which was intuitively designed. And if you ever look at that, you'll see it's a very elegantly proportioned lighthouse, and that in its turn influenced the design of other lighthouses in different parts of the world.
Often working from first principles, the Stephensons did more than anyone else to advance the construction of lighthouses. Their expertise was adopted all around the world. But they were happy to make this lasting contribution to the safety of mankind with little regard for financial gain.
All the improvements were given freely to mankind, I suppose. And it's not as though the Stephensons, in any case, were just building for Scotland. A lot of their material was exported. Lighthouses went to Singapore, to India, to Japan.
If any further evidence is required as to the impact of the Stephensons dynasty, what better proof than the lighthouses themselves?
Let's not forget that the Bell Rock is just coming up to its 200th anniversary, and it is the oldest surviving rock lighthouse in the world. And I think a 200-year stretch for a piece of masonry that's constantly battered by the elements, that's really pretty amazing.
Building a lighthouse, any lighthouse, in the middle of a rock, in the middle of the Atlantic, would be very, very difficult even today. Doing it 200 years ago is absolutely extraordinary. The testament is that they're still standing, they still work, and they still do their job, and they still save lives. Yeah. And you can't really get better than that.
Not only were the crucial advances of the Stephensons, William Symington and James Watt the blueprints for so much of our modern world, but they also signalled a transformation in Scotland's fortunes.
Invention gives Scotland the edge, and again, it's not because we in Scotland have the best resources or the best coal or the best iron, far from it, but we have the best technology.
Technology was changing fundamentally, and many Scots were working at the cutting edge of this brave, new, automated world.
Now, I put that down not to some kind of Scottish genius, but to the very fact of the frenetic pace of industrialism. The buzz, the activity, throws up all sorts of ideas, all sorts of problems, all sorts of opportunities.
Through one such opportunity, a Scottish engineer was about to forever change the way in which metal could be forged and shaped, signalling the birth of precision engineering and revolutionising bridge building and shipbuilding.
James Naismith was an extraordinary guy. He came from Edinburgh, and he wanted to be an engineer, and he studied some engineering up here, and then he heard that the best engineer in the world was Henry Maudslay. Henry Maudslay was the father of precision engineering.
Naismith headed south to join the ranks within Maudslay's factory, which was a hothouse of engineering genius.
Some of the best engineers of the early 1800s came out of that stable, because Maudslay was not only a brilliant engineer but a brilliant teacher. So we had Roberts, and we had Naismith, and we had Whitworth, who invented Whitworth nuts and bolts and so on.
Having completed an exceptional apprenticeship under Maudslay, Naismith started his own foundry in Manchester on the banks of the Bridgewater Canal.
There he was making all sorts of things, steam engines. He made all his own tools. He made his own production line and so on. Wonderful, wonderful man.
Naismith's unique contribution to the modern world came about in the 1830s, when he was consulted on a particular problem by an engineering legend.
Isambard Kingdom Brunel was building the SS Great Britain, the first big iron steamship down in Bristol. And she was going to be a paddle steamer. So she was going to have a huge paddle wheel on each side of the hull. And to drive them, he needed an enormous shaft that went right across the boat from one side to the other and was going to be driven by the engine. Now, this metal shaft was going to be the biggest bit of iron that had ever been manufactured. And his engine builder, Mr. Humphreys, had no idea how to build it.
Such was Naismith's reputation as an engineer. He was sought out by Mr. Humphreys to help overcome this challenge.
Naismith looked at this and he thought, it's a bit of a problem, this, because the hammers they had then to forge iron were basically a hell of hammers. They were hinged at one end and they were lifted either by steam or by water. They went up and then went bonk, bonk like this with their weight. But if you had a very big bit of iron, then they could only go tap, tap, because they didn't have far enough to fall. And they didn't hit vertically either. They're hitting now at an angle. And you could not forge that huge piece of iron with a helve hammer. So what was he going to do? And he sat down and he said within half an hour he had the whole thing worked out. And in his scheme book, he'd sketched it out. And basically he invented the steam hammer. And this was a chunk of iron weighing, 500 or 600 weight, a big chunk of iron, which was going to be blown up by steam pressure on guide rails. And then you open the valve to let the steam out and it drops. And you can blow it up as hard as you want, and you can drop it from as high as you want, and you can do it very accurate and it comes straight down. Brilliant idea.
Having solved this problem and fundamentally improved engineering in the process, Naismith presented his findings to Humphreys and Brunel.
Unfortunately, Brunel by then had fallen in love with the newfangled screw propeller. He'd seen a boat with a screw propeller and he decided he was not going to have paddle wheels after all. So he wrote back and said, no, sorry, we don't need it. So Naismith just didn't build it. And a few years later, 3 years later, he went to France. He went to the Creusot factory in France. And he saw some enormous forgings there. And he was very impressed. And he said, how do you make those? And they said, with your hammer. And he said, what do you mean with my hammer? And the manager of the Creusot factory had been to visit him. And Naismith was away. And the chap looked in his office and saw this picture of in his scheme book. And thought, that's a good idea. And he went and built one in France. So there was a great argument about who'd invented it. But actually, Naismith won and he got the patent rights back.
Naismith's 30 minutes of inspiration that created the steam hammer was to revolutionise heavy engineering. It was now possible to manufacture iron and later steel on a huge scale.
Once you've got that mass of steel, you can then hammer it into shape with a steam hammer, and you can make huge things much more quickly, so that the idea of building huge iron ships or steel ships became feasible.
Like most inventions that have a fundamental and immediate impact, the idea behind the steam hammer was simple and also enduring.
The thing about the steam hammer is it was invented in the 1840s, and it's still in use today. It's now driven by compressed air, not by steam, but it hasn't changed. It is still an absolutely vital tool in heavy engineering.
Not only could this forge metal at scale, it was also incredibly sensitive. So it could crush an egg in a wine glass, but not the wine glass. And really, it's the first machine making another machine.
Naismith's advances sparked a new dawn in heavy industry, allowing engineers to be bolder in their use of raw materials. He paved the way for engineers to create awe-inspiring work. Bigger, longer, and stronger. The scale was epic, and eventually reached its zenith with the eighth wonder of the modern world.
It was Naismith's steam hammer that enabled this fourth bridge to be built in this new material, steel. And the steel was so strong, in fact, that they were able to achieve a span that was greater than the world's longest span suspension bridge. It never ceases to amaze me. It really is the eighth wonder of the world.
The Industrial Revolution was forever changing the landscape of Britain. Projects of unprecedented ambition and scale were commissioned to further this industrial growth. Behind many of these undertakings was a Scot, born into poverty in the borders of Scotland, but who went on to become an engineering colossus.
Telford, I think, is the engineer par excellence of the early 19th century, the man who had both a social vision as well as a technological vision.
Thomas Telford, I think, was a classic Scottish lad of parts, renowned during at least the last 15 years of his life as the most famous civil engineer in the world.
Canals were the vital arteries through which goods were transported to our growing cities. This need for new waterways offered opportunities to an ambitious engineer like Telford.
They needed to have, wherever they crossed a river, they needed to have aqueducts. And all the early canals had very ponderous-looking stone aqueducts, very heavy stone aqueducts.
No feat of engineering was beyond Telford. During the building of the Ellesmere Canal in Wales, he was confronted with a wide and deep valley. The elegant solution typified Telford's genius and ambition.
It is the most extraordinary thing. This canal had to go over the River Dee, and most canals going over rivers were on very solid, low stone bridges. And he said, no, we don't want that. We don't want to go right down the valley. We'll go straight across the top. And he supported it on great big stone pillars. And they called it the River in the Sky. And there was a huge celebration when it opened. And it was the first one that had ever been built at such size and with such elegance and grace.
The achievement there to create an aqueduct using iron troughs and stonework of immaculate quality that's still standing and is relatively lightly maintained even today. It was quite phenomenal. And as a work of art in the landscape, it was admired and acknowledged by Sir Walter Scott, for example, who thought it was the greatest work of art that he'd ever seen.
Telford was also a man of immense social awareness. Telford, for example, in his comments to the 1803 parliamentary inquiry on the Highlands and Islands, revealed a breadth of vision that we tend perhaps not to associate with engineers who are only focused on getting a result.
Such was Telford's reputation that he was the man tasked by the British government with opening up the remote Highlands of Scotland to the modern world. Not only did this demand 900 miles of roads, but the building of the greatest waterway ever attempted.
Well, for the Caledonian Canal, nothing like that had ever been attempted. The enterprise was of a scale equivalent to the Roman aqueducts, and nothing like that since then had ever been attempted. It was a huge, huge civil engineering enterprise, the equivalent of the Channel Tunnel today, for example.
The sense you get from these men is that everything's possible. The sheer dynamic of optimism. I cannot believe we would ever contemplate, even given our technical resources, the building of another glorious fourth railway bridge or another Caledonian Canal. But to these men it was all possible.
I don't think anyone today would build the Caledonian Canal. It would be bonkers, you know. It's obvious when you look at it. I mean, Scotland's almost cut in half, and all you've got to do is a little bit there and a little bit there, and you can get from the North Sea to the Atlantic Ocean. Really amazing. I mean, to sat out doing... And that's blokes with picks and shovels and wheelbarrows, you know.
He was mobilising resources and men and machinery on a scale that really hadn't been attempted since the height of the Roman Empire.
With 900 miles of roads and the mammoth Caledonian Canal, Telford had opened up the Highlands of Scotland to Britain. Following the Treaty of Union with Ireland in 1800, the government would turn again to Telford to improve the links between London and Dublin. The centrepiece of this project would be the construction of the world's longest spanning bridge.
The Menai Bridge is my favourite of all. This is the bridge that links the northwest of Wales to Anglesey, and it goes over about a 300-yard gap, the Menai Straits. It took them 9 months to build that bridge, and it finally opened in January of 1826. And there was tremendous celebration and, you know, bands playing and a traffic jam on the bridge because everyone wanted to cross at the same time. And that was easily the biggest suspension bridge in the world at the time. A really extraordinary feat of engineering. The people in the early 1800s had an extraordinary can-do attitude. At that point, we, Britain, led the world in production of steam and iron, and we just felt we could do anything. At least the engineers felt, yeah, all right, that's quite a big gap, we'll bridge it, we'll build a bigger bridge than anyone's built before. They didn't seem to be frightened of anything.
You cannot underestimate the power and the impact of Telford's achievement in designing and supervising the construction of the Menai Bridge, and its impact resounded across the world, Canada, America. They observed and learned from the Telford Bridge experience and applied it in America for some time.
Telford did more than most to enhance the science of civil engineering. To this day, his bridges, roads and canals remain vital elements of Britain's transport infrastructure. It is no wonder that his death in 1834 was an occasion of national mourning. Telford was honoured in death by being buried in Westminster Abbey.
The engineers of that time, of the mid-19th century, were really the superstars of their day. They were recognised publicly as the great advancers of knowledge, the great creators of new opportunities that created monumental changes to the British landscape.
Another Scot, a contemporary of the great Thomas Telford, was to have a similar impact on 19th century Britain. He would become the central focus in the push to build roads that linked the growing cities of industrial Britain. Roads that had advanced little since ancient times.
Transport's always been vital, and that's been obvious ever since the Romans came here. The Romans came here, they needed to get their army from place to place, and they built these fantastic straight roads. Unfortunately, they left in about 400 AD, and then nobody mended the roads for about 1,000 years. And when we came to the Industrial Revolution, suddenly people were making A, very heavy vehicles, heavy carts, heavy steam carriages, and B, they needed a lot of transport to get goods from A to B, so raw materials to factories and the product out again.
In 1786, John McAdam, fresh returned from America where he had been working in finance, was struck by the poor condition of the roads.
And it became very obvious to him that the roads were in a terrible state And he seems to have entered into a crusade to improve the roads of the kingdom.
McAdam's first venture into road building was on his doorstep in Ayrshire. He constructed a road from the Alloway to Maybole Highway, straight to his newly purchased estate. This small project would be the precursor to fundamental change in travel in Britain.
Travel in those days was mainly by horse. If you had luggage, it got sent by sea. And I think that what McAdam did was develop a network of roads that actually halved the travel time or doubled the speed.
Already a man of substance in 1801, McAdam was appointed surveyor to the Bristol Turnpike Trust, one of the bodies who collected tolls for the upkeep of the roads. At the time, approaches to maintaining the roads were extremely primitive.
When there was a great hole in the road, what they would do was go to a quarry, get a load of stones and dump it in the hole. Now, obviously, that's going to be horribly lumpy. And the next carriage, and these are carriages with iron tyres, would go scrunching over it and break some of the stones up and some would fall off. It was a nightmare. And he reckoned that what you needed to do was to get stones from the quarry and break them up. And you wanted to get stones, eventually, that were small enough to go in your mouth. And he would hammer them down, big stones at the bottom, and then these ones, quite small, hammer down on top, and maybe a little bit of gravel on top. And he said the road should be 18 feet wide, and it should be 5 inches higher in the middle than at the outside, so it had a nice camber. And if you hammered it down flat, then all the rain would run off, and it would stay dry, and it would stay hard, and it wouldn't be broken up by carriages going over it. And it worked incredibly well. And indeed, there was then an Act of Parliament to say that all roads in Britain should be macadamised. His name went into the literature.
McAdam's new roads increased the pace at which industrial Britain could function. This improved travel meant business could be carried out much quicker, but communication also benefited.
The post office network had relied on horses up until that point. Suddenly they were able to actually move mail quickly and efficiently by carriage. And there was suddenly a network of public transport. You did not need to own a horse to be able to travel around.
The rapid changes in Britain's roads were due to the crusading zeal of McAdam, allied to his practical designs. But he was also a man who saw profit in his position.
The way that McAdam made his money was that there were so many small turnpike trusts that he was actually getting appointments as surveyors, he and his family, to so many of them, and they were each paying him for the privilege of being a surveyor.
Macadamisation became the national standard, not only in Britain but globally, with America becoming infatuated with the creation of vast highways. McAdam's legacy was to transform the muddy tracks of the Dark Ages into a network that sustained and maintained the accelerating modern world. Today's roads have altered little since the days of McAdam, with the exception of one vital ingredient, the inclusion of which appears to have been the result of a happy accident.
I gather that in 1901 there was a wagon near I think it was the Denby Ironworks in Derbyshire. It overturned and a barrel of tar fell off and broke on the road, and there was this horrible sticky mess right across the road. Well, fortunately, it was an ironworks and they had a whole lot of slag, and somebody put a lot of slag on top of the tar, and it all settled down. And that was a lovely smooth road. And they thought, oh, that's a really good idea. And so they formed this company called Tarmac, obviously calling it Tar Macadam because macadamised roads had become the national standard. So that's how Tarmac started, but it was nothing to do with Macadam.
Britain's improved roads opened up travel to more people than ever before. But the only viable means of transport remained the horse and carriage. In the 19th century, there was a desire to make man self-sufficient. The answer was the bicycle.
The development of the bicycle really started in Germany in 1817 when Karl von Drais invented the hobby horse. They became a sort of plaything of the rich. You sat astride this thing, you paddled along, and it was ideal for the rich dandies of the time to go out to the local park and show off.
What started as a fun invention for rich Europeans with money and time to spare evolved to become the most efficient machine ever built. And it is in Scotland that a great technical leap forward was made in the development of the bicycle by an artisan blacksmith.
The first person who realised that you could both simultaneously balance one of these things and propel it was probably Kirkpatrick Macmillan in southwest Scotland.
Well, this is a Macmillan machine built by Kirkpatrick Macmillan in 1839. It's significant because it's the first true pedal cycle. It's built with wooden wheels, much like a cart, so you can hear it's fairly noisy, and on this tarmac road, fairly easy to ride.
Macmillan may have worked as an artisan blacksmith in Dumfriesshire, but this young man had served an apprenticeship under the great engineer Robert Napier and was attending night classes to further his knowledge.
He was actually learning and probably being encouraged at night school to actually develop ideas and to experiment.
Macmillan's experimentation was to take the principle of the dandy horse and transform the device by adding driving gear and pedals, allowing the rider to propel himself forward.
It was a machine in which he could go into Dumfries, go around the countryside, but he never conceived of it as a commercial thing that he might actually produce, build and sell. He did it for his own fun and his own enjoyment. He wasn't ever commercial, so he wasn't advertising them or selling them.
Macmillan had provided himself with a machine that could transport him 70 miles from Dumfries to Glasgow in 2 days, a time only rivalled by a man on horseback. However, it's this legendary trip to Glasgow that is now at the centre of a continuing debate as to who rightfully invented the bicycle.
So the story goes, somebody else who actually saw him on this famous ride that he did to Glasgow, he rode to Glasgow over 2 days, saw this machine, copied it, and then claimed it as their own.
The gentleman who was rumoured to have copied Macmillan's machine was a Mr. Gavin Dalziel. The first evidence of Dalziel's machine appears in 1846. However, an article from 1842, unearthed by cycling enthusiasts, could hold the key to establishing which bicycle came first.
They were able to uncover this story in a Glasgow paper, because when he rode to Glasgow over the 2 days, when he finally got to Glasgow, he had a collision on the pavement with a child, and he was taken to court and fined 5 shillings for that incident.
This early traffic offence would appear to be convincing evidence for the Macmillan camp. But with neither Dalziel or Macmillan pursuing a patent for the machines, it was only a matter of time before another prototype bicycle would emerge.
It was another 25 years, and it was in France when the Michaud family put pedals on the front wheel, and the bicycle then became a commercial success.
Pedals on the front wheel combined with driving gear attached to the back wheel would soon evolve into what we now recognise today as the modern bicycle. Like so many Scottish engineers before him, Macmillan made a decisive contribution in the creation of a global phenomenon.
Nowadays, the bicycle in this country has become a leisure machine, but in many parts of the world, it's a means of transport, and possibly the only means of transport for many people. And as the bicycle in the sort of 1860s started to come in, people started to spread their horizons. The idea of going 14, 15 miles from home would be unheard of. But on a bicycle, you can start to tour. And in the 1880s, people were touring all over the country on massive tricycles, all part of a development from Macmillan's original machine.
By the late 19th century, the bicycle had become a mainstay of Victorian culture. But on primitive roads and unforgiving steel tyres, it was still an uncomfortable ride. But one enterprising Scot would bring this discomfort to an end.
John Boyd Dunlop, another Scot who'd become a vet and moved to Belfast, his son Johnny used to ride to school on a tricycle. And it was horrid because all the streets in Belfast were cobbles and it was very uncomfortable. He complained his bottom was sore. And so John Boyd thought, I know what, I'll give him nice soft wheels. And so he got a rubber tube, like a sort of hose pipe really, and fixed it round a wheel with allegedly strips torn from one of his wife's skirts, nailed on, and he pumped it up and sent his son off. And his son said it was wonderful, it was very comfortable, and what's more, he was quicker than all his mates. And everyone thought, oh, nonsense, it's a load of rubbish. But John Boyd Dunlop thought, oh, well, there might be money in this if it really is quicker.
Dunlop's belief in his tyres was to pay off. He paid a local boy racer by the name of Willie Hume to try these new tyres at a race event in 1889. Hume won by a country mile, but most significant were two young Dubliners he left trailing in his wake.
They were the sons of a great newspaper magnate, so they wanted pneumatic tyres at once. And they took them to England and they won every race they were allowed to enter for. And then everyone wanted pneumatic tyres.
Dunlop took out a patent on his air-filled tyres in 1888. But 2 years later, it was declared invalid. The pneumatic tyre had already been invented and patented 4 decades earlier by another Scot.
Robert Thomson, he was the true inventor of the pneumatic tyre. He was born and brought up in Stonehaven and had come up with this idea of having inflated tubes within an outer cover. And he demonstrated this in 1847 in Hyde Park.
He had 2 identical carriages pulled by horses, and one had solid iron tyres and one had his aerial wheels. And the first thing people noticed was that his aerial wheels were silent. And that was, really impressed the passers-by. And the second thing was that they needed much less effort to pull them. He actually measured what he called the draft, the amount of effort needed to pull one of these cars. And with his aerial wheels, it was much less than with the solid iron tyres.
Despite the success of the trial, at £42 a set, the equivalent of £30,000 today, the costs of Thomson's aerial wheels were prohibitive. Discouraged by the lack of demand, he abandoned his invention and returned to developing solid rubber tyres.
I think had Thomson continued development of it, then he may have got to the stage of actually having a single tube, which is what Dunlop came up with, which meant that there was a single inflation point and it was workable. But again, it's about demonstrating principles, and it demonstrated quite dramatically how much benefit you got from an air-filled tyre over a solid tyre.
With Thomson leaving his early invention behind, the path was clear for the younger man, Dunlop, to perfect the pneumatic tyre. Improved technology in rubber manufacturing and increased demand meant that by the end of the 19th century, the pneumatic tyre was here to stay.
They are much more efficient, they're quieter, they just make life a whole lot better for all rolling stock. And it's just very bad luck on Robert Thomson that he was too early, he was ahead of his time.
Despite the failure of his aerial wheels, the brilliance of Robert William Thomson never diminished. He went on to invent the vertical steam boiler, a portable steam crane, and pioneered the use of electric charges in detonation. Foresight and vision are hallmarks of invention. By the late 19th century, Britain's transport network was extensive and, with the exception of the motorway, almost identical to what we use today. But it could all have been so different if one Scot could have realised his vision of the future.
George Binney was a Glasgow inventor, really, who had a vision for a new type of transport, using existing technologies, but combining them in a very unique type of way. So what he did was he made a monorail which had carriages hung beneath it, but he used not steam engines, but propellers, like you find on planes at the time.
An early collaborator was the London and North East Railway, who allowed Binney to use a 400-metre stretch of track in Mulgai near Glasgow to test his futuristic vision.
Binney's opinion was that since you had the existing railway lines, you just have to build these structures on top of those railway lines. So it's a steel A-framed structure, to be very simple. And then that would go over the existing lines, so the West Coast Main Line, or somewhere between Liverpool and Manchester, or Blackpool and Southport, which had been suggested. So it was his opinion that it wouldn't be that much of a struggle to get these built because the lines had already been built in many places.
Piggybacking on Britain's existing rail network was inspired and also pragmatic. But to have these rail planes thunder around the country at double the speed of locomotives would require aviation engines, an industry still in its infancy.
His first patent was in 1923 for this. Now, if you think that's only 20 years after the Wright brothers flew in a very simple, very light airplane. So he was a visionary in that kind of way.
The launch of Benny's railplane in 1930 was a great success and was hailed as a wonderful product of British brains. But he was now looking for major finance during the worst depression the world had ever witnessed, and investors were suddenly lacking confidence.
Getting new kind of investment to build an untested and untried kind of system proved impossible for Benny, both home and abroad. He did have areas in the United States and the Middle East interested, but ultimately no one could either afford or wanted to try a new system that hadn't had any background or testing.
George Benny doggedly pursued his railplane system until 1937, when he was finally declared bankrupt. But many of the problems his vision could have solved remain with us today.
He was trying to create a new kind of system of transport. That vision that he had in 1923, or even earlier than that, is still something we're searching for today, that the railways in Britain and across the world are searching for better ways to get more capacity on the railways, and more railway carriages, or less freight trains, or those in the middle of the night, and so on. So it's not something that was just in his head. That wasn't a problem then. It was a problem then, and it's a problem now that still has to be solved.
Benny died in 1957, without witnessing elevated railways and monorails becoming regular features in cities across the world. His neglected vision showed the unforgiving margins between success and failure for those who want to make their mark on the modern world. In the 20th century, Scotland and its engineers no longer experienced the preeminence enjoyed throughout earlier centuries. Not for a want of skill and ingenuity, but because Britain's position as world leader began to recede.
Historians always have the great advantage of hindsight, and you can say that from 1870 there's been a decline, and the reason for that is basically that's when the Scots stopped being the major inventors. You know, for example, in the shipbuilding, the Daimler and the diesel engine took over from all this. The Germans took over. That's one argument. The other argument is the belief that bigger is better, and everything should move into bigger and bigger states, and therefore companies should amalgamate, and you get the rise of the multinationals.
But with a collapse in global credit markets and dire warnings over dwindling resources, is there an opportunity for Scotland to regain a competitive edge, exploiting the very sources of power that the advances of the Industrial Revolution supplanted?
When the technology is harnessed, the Western Ocean is going to be phenomenal, both in wind and wave power, but also the oil resources. So there is a certain drive now. There's also the imperative of global warming, which is driving technology. And in one way, we could be returning to a new age of enlightenment and invention.
And the series concludes next Tuesday at 9 here on BBC Two Scotland. Tomorrow at 9, Andrew Marr investigates the making of modern Britain. Details coming up.